All right, so today we're going to learn another integration technique called integration by partial fractions. So this is usually when you have a rational function and it has a polynomial in the numerator and a polynomial in the denominator. You just want to make sure like old methods don't work, like checking normal u and du, like where you try to make u the denominator and du ends up being the numerator, except for maybe a number. Always check that first and then watch the powers. If the powers are the same or the power's bigger on top, what do you have to use? Right, long division. Okay. All right, so with partial fractions, all right, remember, you're looking at this. There's nothing else that you can do. It's not a regular u and du problem. The power is bigger on the bottom, so it's not long division. So what you're trying to do is this came from two fractions. So back in like algebra 2, you learned that when you were adding or subtracting rational functions, you wanted to make it one rational function by finding a common denominator. Well, this is like the end result, and what we're doing is we're finding the two rational functions it came from. So we're going backwards. So what you want to do is factor the bottom if you can. That's another sign that this is integration by partial fractions if you can factor the bottom. This factors into x minus 2, x minus 3. So what you're going to do is you need to find the numerator of each one of these fractions. So the first one has a denominator of x minus 2. And then we're going to add it to the second one that has a denominator of x minus 3. Now, these are called linear factors because it's degree 1. Okay, linear factors because it's degree 1. So in the numerator, it has to be one less degree than the denominator. So if this is degree 1, the numerator is degree 0, which is just a constant. So A and B just stands for just constants. Now, what we want to do is something called the cover-up method. All right, and the cover-up method only works for linear factors. Okay, only works for linear factors. It's a very easy method. So basically what you do is if you want to find out what A is, you ask yourself what x value makes the denominator of A's fraction go to 0? That would be x equals 2, right? If I plug in 2 here, it would make the denominator go to 0. So what you're going to do is you're going to cover up, and I'm going to have to do that. We're going to cover up that factor on the bottom and plug in x equals 2 anywhere we see x's. So if you had x's in the numerator, you plug it in there, but you don't. So you would plug it into the denominator, and you end up getting 1 over 2 minus 3, which gives you negative 1. So you just found out that A is negative 1. It's that easy. Okay? Now, so I'm going to have to erase this. Bear with me because I got to rewrite it. This is obviously easier if I did it on the board. This is x minus 2. Okay. So if we want to find out what B is, you ask yourself what x value makes the denominator of B go to 0. That would be x equals 3. And what you do is you cover up the x minus 3 factor, and you plug in 3 anywhere else you see x's. Well, there's no x's in the numerator. It's just 1. If you plug in 3 here in the denominator, you get 3 minus 2, which gives you 1. So you just found that B is 1. And there you go. You just broke this fraction into its partial fractions. So the fractions it came from, this one right here is negative 1 over x minus 2. So we're going to integrate that. Plus, the second fraction is 1 over x minus 3. And now you integrate each one of these separately. So like back in algebra 2, you were given negative 1 over x minus 2 plus 1 over x minus 3 and said to simplify it, meaning making it one fraction, which you would end up getting back this right here, okay? So now you integrate. You're making u the denominators, your du's or dx's. There's nothing that you need to put in. Same method for both of these. All right, this first one here, you can pull out the negative. You get du over u. Plus the second one, when you integrate, you get du over u. Okay, and both of these become the natural log of the absolute value of u plus c on the end. There you go. Okay. All right. The next one. Once again, you're checking to see if you make u the denominator. It won't work because you don't get du in the numerator. It's not long division because the power is bigger on the bottom. So what you want to try to do is factor next. So factor the denominator, you get x times x squared plus 2x plus 1, and you can keep going here. This factors into x plus 1 times x plus 1. These are repeating linear factors, right? The x plus 1 repeats. So this is how you write out your partial fractions. The first one's a over x, the first factor on the bottom here, plus the second one, and the last one would be c over x plus 1 squared. You want to show the progression of your repeating linear factors. If you have two of them, your last denominator is x plus 1 squared. If you had a third one here, it would be plus d over x plus 1 cubed. Okay? So with repeating linear factors, you have to show each power. So x plus 1 to the first and x plus 1 squared. Now, we need to find a, b, and c. Okay, just like we did in the last example. And we can use the cover-up method for linear factors, but you have to watch out for repeated linear factors. For repeated linear factors, the cover-up method only helps you find the one with the highest power. Okay, the cover-up method only allows you to find the constant or the numerator of the highest power, and you'll see why in a second. Okay, so what x value makes the denominator go to 0 here? That would be x equals 0. So what you do is you cover up this x, okay? I don't want to cross it off because then I got to erase it. So you cover up this x, and you plug in 0 for the remaining x's. So on the top, you plug in 0 here, 0 here. You're just left with 6. Okay. Look at this factor form. When you cover this up and you plug in 0 to the other two x's here and here, you get 1. So you get a is 6. Now, we said using cover-up method is not going to work for repeating linear, the lower power one. This is to the first, this is to the second. This is why. If you go to try to solve for b, you would say what x value makes the denominator b go to 0? That would be negative 1. You'd only be crossing off one of these. So when you go to plug in negative 1 to your remaining x's, the numerator won't matter, but the denominator, look, you could be plugging negative 1 into this one also, which would give you 0 in the denominator. So you can't solve for b using the cover-up method, but for c you can. So once again, x equals negative 1 makes the denominator go to 0. What you're covering up is both of these. So when you do that, in the denominator, the remaining x would be negative 1. In the numerator, when I plug in negative 1, we're going to get 5 minus 20, which is negative 15, plus 6, which is negative 9. So we get c is positive 9. Okay, So this is what we have so far. I'm going to write this out. So the left integral, and bear with me because it takes me forever to write with this. I'm going to make it x plus 1 squared. We know that that is equal to 6 over x plus b, we don't know it yet, over x plus 1 plus 9 over x plus 1 squared. All right, and what we're trying to do here is solve for b. So all you're doing is using your algebra skills, and perhaps I should have just not put this integral here. I don't want that to confuse you because you're really not integrating yet. We're just doing algebra. So we are going to multiply both sides by the common denominator. The common denominator is x times x plus 1 squared. Right? Do that on both sides. X times x squared. So when you do that, you're left with 5x squared plus 20x plus 6 on the left equals, okay, so this 6 over x, the x's will cancel, so you're left with 6 times x plus 1 squared, plus the b needs an x and another x plus 1, plus the 9 needs the x. Okay, so what we're going to do is multiply out the right-hand side. Like I said, this is not hard. It's just algebra and a little time-consuming, but it should not be anything that's super difficult. So here we get 6x squared plus 12x plus 6 plus bx squared plus bx plus 9x. That equals 5x squared plus 20x plus 6. And you know with an equation, the left side has to equal the right side. We want to know what b is equal to. So you can choose what terms you want. I'm going to work with the x squared terms. So the x squared terms on the right should equal the x squared terms on the left. So technically, 5x squared on the left should be equivalent to all the x squareds on the right, which is 6x squared plus bx squared. And when you go to solve this, you can cancel all the x squareds and solve for b. You get b is -1. There you go. Now, did you have to use the x squared terms? No. You could have used the x terms. So 20x should equal 12x plus bx plus 9x. Look what happens. 20x should equal 12x plus bx plus 9x. Okay? All the x's will cancel. You get 20 equals 21 plus b. When I go to solve for b, my b equals -1. Okay, so either way, you can get what b is. You don't have to do it both ways. Just choose one. So now we have a, b, and c. Now we go and plug those back in and integrate. Let's see if I can get some more room here. Okay, so the last part of this is your a is 6 over x. That's your first integral. Plus your b is -1 over x plus 1. And your c is 9 over x plus 1 squared. Okay, we should be experts at both of these turn into d over u. So this is 6 ln absolute value of x minus, pull that negative out, ln absolute value of x plus 1. Now I got to be careful. You're making u x plus 1. Your du is dx. You don't have to put anything in, but this is going to be integrating. If you pull the 9 out, u to the negative second. Be careful with that. That is 9u to the negative first over negative 1. So this is actually negative 9 over u, and u is x plus 1 plus c. And this is all old stuff. That's not anything new. It's something you learned in the past in chapter 4. What's new is dealing with something where you got to factor denominator, find the partial fractions a, b, and c in this case, and then integrating. So once again, if it's a linear factor, piece of cake, you use the cover-up method to find your constants above. If it's a repeating linear, you can only find the constant of the highest power. To find the other one, you multiply through by the common denominator and compare the left side with the right side. All right, now with number 3 here. So remember, you're not like, I don't want to be doing partial fractions unless I absolutely have to. Okay, so with number 9 here, does u and du work? What would I make u? The bottom. The derivative would be 2x plus 2 dx. And that's basically the numerator with a times 2. So I put a 2 in, and if I put a 2 in, what goes on the outside? 1/2. So this literally is du over u, okay? And so that integrates to the natural log of the absolute value of u plus c. Now, could you have done this with partial fractions? Yes. But why would you want to do that? Make it a lot harder. Okay. All right. So on to the back part here. Okay, 2 more examples. Linear and quadratic factors. So, all right, remember the cover-up method can only be used for linear factors. This is already factored for you. That kind of gives it away that this is probably going to be partial fractions. In fact, if you can factor more, do that. So this factors more into x times x minus 1, and then x squared plus 4. This is the first time we're seeing a quadratic factor, meaning degree 2. So here's how we write it out. A over x, this is linear, so then this is just a constant, plus b over x minus 1. Remember, this is, or x minus 1, I wrote plus 1. All right, this is linear, then this would be degree 0, which is a constant. And then this is the first time you're seeing a quadratic factor. So x squared plus 4. So if it's quadratic on the bottom, it has to be linear on the top. So linear would be cx plus, and then you should have a constant d also. All right, so if this is in the form of quadratic, then your numerator would be a constant times x plus another constant. Okay. Now, we want to find a and b using cover-up method, because you can, because they're linear factors. The denominator of a go to 0, that would be x equals 0. So you're covering up the x in the denominator. Cover that up. And you're plugging in 0 for all the remaining x's. So if I plug 0 in the bottom, or sorry, 0 in the top, I'm going to get negative 8. Over, remember, I'm covering this up in the denominator. Now I'm going to plug 0 here and 0 here. I'm going to get negative 4. So that gives me a is 2. Here's your first one. Sorry, this is being slow. It's not letting me change colors. Okay, there we go. Put my x back in there. Okay. So to find out what b is, what x value makes the denominator of b go to 0? That would be x equals 1. So I plug in 1 to the numerator x's. So it's going to give me negative 2 minus 8 is negative 10. Over, if I plug in 1 in the denominator, remember, this one's crossed off because I'm covering up that factor. And I'm plugging in 1 everywhere else, that's going to give me 5. So b is -2. Okay, so let me erase this. All right, and this C and D I can't find because it's quadratic, and you're going to have to do some algebra to find C and D. Okay, you can only use cover-up method for linear factors. So I'm going to set the inside of the integral on the left equal to what I have on the right. So A is 2 over x minus 2 over x minus 1, and then plus cx plus d over x squared plus 4. Okay, so what we do now is we multiply through by the common denominator, okay, on both sides. The common denominator is x times x minus 1 times x squared plus 4. I'm not going to write that over here on the left because what's going to happen when I write it over here, it cancels with the denominator down here. So all you're left with is 2x cubed minus 4x minus 8 in the numerator. Okay, on the right-hand side, when I multiply through by the common denominator, the first 2 gets the x minus 1 and the x squared plus 4. Minus the second 2 gets an x and an x squared plus 4. And the last part, cx plus d, it gets the x and the x minus 1, which I'm going to write that out as x squared minus x. It's easier. And now what I'm doing is I'm taking my time and I'm multiplying this all out. Okay, I'm taking my time and I'm multiplying this all out. Okay, so it takes a little time to multiply this out on the right. So we're going to get 2x cubed, okay? Then when I do x times 4, that times 2 is going to be 8x. Minus 1 times x squared is negative x squared times 2 is negative 2x squared. Minus 4 times 2 is 8. Let's see. Did I miss something? 2x cubed. Okay. The next one is negative 2x cubed minus 8x plus cx cubed minus cx squared plus dx squared minus dx. I'm literally just foiling here. Okay. All right, now we're comparing the left side with the right side. I need to find C and D. C and D are my goals. So I usually start with the highest power on the left. So 2x cubed equals 2x cubed minus 2x cubed plus cx cubed. So 2x cubed equals x cubed plus cx cubed. So then these are going to cancel. You can divide through by x cubes. So you get c equals 2. Okay. And now I want to find out what d is. So, I mean, I could go down to the x squareds if I want. There's 0x squared on the left. So you could say 0x squared equals negative 2x squared. Maybe I'm looking at this. Negative 2x squared minus cx squared plus dx squared. Okay, and you could cancel all the x squareds. You know that C is 2 from the previous part. So it looks like D is 4. All right, you didn't have to use the x squareds. You could have used the x's and said negative 4x equals 8x minus 8x minus dx, and solve for d and gotten 4 that way too. It's totally your choice. Okay, but the left side of the equation terms need to equal the right side of the equation, the like terms. All right, so now that we have A, B, C, and D, now we go back and we actually integrate this. Okay, so being that I have room, we're going to integrate A, which is 2, so 2 over x, and minus, I'm going to just pull the negative out right now, minus 2 over x minus 1. And then the last part, plus c is 2x plus d, which is 4, over that denominator, which is x squared plus 4. And now we're going to integrate each one separately. This first one here becomes 2 ln absolute value of x minus the second one is 2 ln the absolute value of x minus 1. You can go right into that if you recognize this is just going to be du over u for both of these. Now, this one right here, that's a technique we just learned or we just reviewed. You're going to split that up, and I'm going to work over here into 2x over, come on, x squared plus 4 plus 4 over x squared plus 4. So we're rewriting it as the sum of two quotients. This one right here is du over u, and you don't even need to add anything in because your 2 is in there. So that becomes the natural log of the absolute value of x squared plus 4. I don't know why this is so slow. And then this one here is arctangent. Okay, that's du over u squared plus a squared. Okay, so your u squared is x squared, your u is x, your a squared is 4, and your a is 2. So you would pull the 4 out. Okay, when you pull the 4 out, you're integrating du over u squared plus a squared. And that integrates to 1 over a. So if I have the 4 out and I do 1 over a, that's just going to be 2. Arctan u, which is x, over a, which is 2, plus c. Oh, this is so annoying that it's so lagged behind. All right, and there you go. So this whole thing right here is your answer. Okay, just got to take your time. All right, last but not least, what do you do when you have repeated quadratic factors? Okay, so remember, all other techniques don't work. You're trying u and du first. You're seeing if you need long division. If that doesn't work, then most likely if you have polynomials, it's integration by partial fractions. This here are quadratic factors, so that means you can't use cover up at all. So, and because they're repeating factors, you have to show the progression, just like we did with the linear repeating. So it would be x squared plus 2 to the first and x squared plus 2 quantity squared. And then in the numerator, you have one less degree, so it's linear. So ax plus b is the first numerator, and cx plus d is the second numerator. You cannot use cover-up method at all. So what you go right into doing here is multiplying by the common denominator. So that's going to be x squared plus 2 squared on both sides. Okay, so I would do that over here too. All right, when I do that, I'm just left with the numerator on the left. And on the right, ax plus b has to be multiplied by x squared plus 2, because that's the missing for the common denominator. And cx plus d just stands alone because it has the common denominator. And then what you do is you multiply out what you can on the right-hand side, and then you're going to compare it to the left-hand side. So we get ax cubed plus 2ax plus 3, or that's not a 3, that's a b, x squared plus 2b, and then plus cx plus d. So our goal is to find out what a, b, and c is. I'm going to start with the highest power, which is the x cubed. So 8x cubed equals ax cubed, and there's no other x cubed. So 8x cubed equals ax cubed. So a, it's pretty easy, has to equal 8. All right, the next one, I don't have any x squared terms, so I'm going to say 0x squared, I don't have any on the left, equals bx squared. Well, there you go. B is 0. That happens sometimes where a constant ends up being 0. All right, moving on to the x terms. 13x equals 2ax plus cx. So 13x equals 2ax plus cx. All right, let's cancel all the x's now. We know a is 8, so if I plug that in here, I get 16 plus c. So c ends up being -3. And last but not least, we're going to try to find out what d is. I don't have any constants on the left, so that's 0 equals 2b plus d. So if b is 0, that knocks it out. So then d must also be 0. So there you go. So now we're going to plug it back in. So we have the integral of, I'm plugging a and b back in here. So 8x and b 0. So you don't have to put anything there. Over x squared plus 2. So that's our first integral. Plus the integral of cx. So c is -3. And d is 0, so I don't even need to put that in, over x squared plus 2 quantity squared dx. All right, and so we're integrating both of these. So the first one, when we integrate, we're making u the denominator, du would be 2x dx. So I'm going to pull the 8 out, put in the 2 that I need, and multiply by a half on the outside. So that's just 4 du over u. All right, this one right here, once again, I make u the inside of the parentheses. Du is 2x dx. I don't want that -3 in there, so I pull it out. I put the 2 in that I need, and the 1/2 on the outside. So you get -3 halves. The integral of, this is not du over u, it's du over u squared. So bring that up, make it u to the -2nd, and integrate it like I showed you on this already. 4 ln Okay, this right here ends up being -3/2. When I integrate u to the -2nd, it's u to the -1st divided by -1 plus c. So you get +3/2. U goes on the bottom, so x squared plus 2 plus c. And here's your final answer. Okay, so there you go. Integration by partial fractions. Couple things. Your power on the top is always 1 less than the power on the bottom. If it's linear, then it's just a constant on the top. If it's quadratic, then it is linear on the top, okay? You can only use the cover-up method for linear factors, and if it's repeating linear, you can only use it for the power that's the highest. Then you just have to do algebra and multiply through by the common denominator. If you have no linear factors at all, like the last one, you just go right into multiplying through by the common denominator. All right, and then compare the left side to the right side to find your constants and then integrate in the end.